Oh, look, an electrical outlet. Now, I know everyone wants to stick their fingers in the electrical outlet, but you should not. Mm-mm-mm-mm. Why? Well, do you see those two prongs? One, two. They are apart by 120 volts. That means that if I stick my fingers in there and charge flows, every coulomb loses 120 joules of energy. And where does that energy go in this case? Into me. That is not fun. It would hurt. Let's talk about it more.
So let's talk about why you shouldn't stick your finger in an electrical outlet. So here's the standard shape of an electrical outlet. This hole, you all know what it is. It's ground. We talked about ground before. It's the place where all the extra charge can go. Now we have two prongs that any electrical device has, one bigger than the other. The big one is called hot, and the little one is called neutral. They're different by 120 volts. That means that for every coulomb of charge that travels from one to the other, it loses 120 joules of energy. Now, we shouldn't stick our fingers in the electrical outlet, because let's say you stick this finger and this finger in. That means that the current is going to flow from one to the other and have to lose 120 joules in that short distance. All that energy is going to go into your skin and probably give you a pretty bad burn. What if we did it the other way? Stuck one finger or one hand in and the other finger or the other hand in. Well, then it's going to go across your body. And notice what's in the way there. Your heart. And what do muscles in your heart and other muscles run on? Electricity. That could easily kill you. Let's not do that. So, we're dealing with this guy, Georg Ohm. I know, awesome name. Georg Ohm found that for many materials, not all, oddly, if you increase how much voltage there is between the start and the end, then the current increases. That's pretty obvious. But what was neat about it was that it was linear. If you doubled the voltage, the current doubled. If you tripled the voltage, the current tripled. If you had the voltage go backwards, the current went backwards. And it followed a pretty straight line for many materials. What that means comes down to voltage is proportional to current. Ohm said that proportionality, I'm going to give that a name. I'm going to call that resistance. Notice not every material does this. Lots of metals do follow this. Pickles follow this. Silicon, germanium, some other odd things called semiconductors don't. It's kind of weird. When we think about current, we can think about water. Water is a really good way of thinking about analogies here. You can imagine that battery as a pump pushing the water. The harder the battery pushes, the harder the voltage is, the more current we're going to get. We can imagine the flow of water as the current. More water is more current. Bigger pump, stronger current. What's the water in this case? What's the individual charges? Your positives moving through your wire. And the pipe? Well, that's your wire. But what the heck is resistance? Well, it turns out resistance is just this idea of difficulty to flow. Exactly what the name implies. It kind of fits perfectly. Different materials, different shapes are going to have different resistances. Copper works a lot better than a pickle.